You know, there's a magic trick that happens all around us, every single day. And no, it's not some kind of sleight of hand. It's actually a fundamental law of physics. So let's dive in and break down what's really going on here.
I mean, we've all seen this, right? You stick a perfectly straight pencil or a straw into a glass of water, and bam, it looks like it's snapped in half right where it hits the water. So what is going on there?
And you know what? This isn't just about pencils. It's the same reason a swimming pool looks way shallower than it actually is, or why a lemon dropped in a glass of water suddenly looks enormous. It's even the cool party trick where you can make a coin appear in an empty bowl just by pouring water in. The thing is, these aren't separate illusions. They are all, and I mean all, caused by the very same scientific principle.
Okay, so what is this one single concept that ties all these weird visual tricks together? Well, let's put a name to it.
The big name for this is refraction of light. All it means is that when light passes from one transparent thing, like air, into another, like water or glass, it changes direction. It bends. That's literally it. The broken pencil isn't broken at all, it's just the light from it taking a little detour.
Okay, so here's where your brain gets tricked. See, your brain is kind of hardwired to assume that light always travels in a perfectly straight line. So when the light from the part of the pencil that's underwater bends on its way to your eye, your brain, well, it doesn't know about the bend. It just traces that light ray straight back and ends up seeing the pencil somewhere it isn't. You're basically looking at a ghost image, a trick of the light.
Now this bending, it's not just happening randomly. Oh no, it follows a very specific, predictable set of rules. And once you get these rules, you can predict exactly how light is going to act pretty much every time.
And the rules, they're actually super simple. It all comes down to an imaginary line called the normal. Just think of it as a line drawn straight up at a 90-degree angle from the surface. So when light goes from air into something denser, like water, it bends towards that line, and when it comes back out of the water into the air, it bends away from it. Towards on the way in, away on the way out. Simple as that.
Okay, so this whole thing is summed up in two basic laws. The first one is easy. The incoming ray of light, the bent ray, and that normal line, they all sit on the same flat 2D surface, like they're drawn on a piece of paper. But the second law, that's the real game changer. It says that for any two materials, say air and water, the relationship between the angle the light hits at and the angle it bends to is always a constant. It's a fixed ratio every single time.
And this super reliable relationship, it has a name, Snell's law. Now don't get hung up on the formula you see here. The big idea is just that this bending isn't chaotic. It's governed by a precise mathematical rule. We can actually calculate it. So it's not magic, it's just math.
All right, so we know light bends. We even have rules for how it bends. But that leaves the biggest question, right? The why. Why does it bend at all? Well, the answer is actually pretty straightforward.
And here it is, the big aha moment. The ultimate reason light bends is because it changes speed. That's it. Think about a car driving from pavement onto a muddy field at an angle. The first wheel to hit the mud slows down, right? But the other wheel is still on the pavement, going fast. That difference in speed forces the whole car to pivot and change direction. Light does the exact same thing. When it hits a new medium like water, it slows down, and that forces it to bend.
So how do we measure this slowing down effect? Physicists use something called the refractive index, usually just shown as the letter n. It's just a number that tells you how much a material puts the brakes on light. The higher the refractive index, the slower light travels and the more it bends. Air has a refractive index of just about 1, but when you get into other materials, that number starts to climb and the bending gets way more noticeable.
Just take a look at these numbers. Water's refractive index is 1.33. Glass is a little higher, around 1.52. But then, check out diamond. It's all the way up at 2.42. That is a huge difference. It means light slows down to a crawl inside a diamond, forcing it to bend and bounce around like crazy. That, by the way, is a huge part of what gives diamonds their famous sparkle.
Okay, now I have to clear something up because this is a really common point of confusion. The word density gets thrown around, but in physics it can mean two totally different things.
When we're talking about light bending, we're talking about optical density. That's just a fancy term for its refractive index, how much it slows down light. This has nothing to do with mass density, which is what we usually think of as density, how heavy something is. And here's the key. They are not the same thing. You can have something that's optically dense, but not very heavy at all.
And here's the perfect proof. Let's look at kerosene and water. We all know kerosene floats on water, right? So its mass density is lower, it's lighter. But, and this is the cool part, its refractive index is actually higher than water's. That means kerosene is optically denser. So even though it's the lighter liquid, it slows down light more than water does. That right there proves that optical density and mass density are two separate ideas.
So let's tie all this together. What's the big idea here? How does understanding refraction actually change how we see things?
When you really think about it, it comes down to this incredible idea. You never actually see an object. What you see is the light that has bounced off that object and traveled to your eye. Your entire picture of the world, everything you see, is built by your brain interpreting the paths that light has taken. So it makes sense, right? When that path of light gets bent, your perception of reality bends with it. The pencil was never broken. It was your perception of the pencil that was.
And that really leaves us with a fascinating thought. I mean, if light can bend this much in a simple glass of water, just imagine where else it's bending and twisting and shaping the world you see every day. That shimmer you see above a hot road, that's refraction. The reason stars twinkle, refraction. It's happening all around us, all the time. Makes you wonder, what other illusions are hiding in plain sight?